Hi, my name is Siddharth Borkar. I'm a junior, and this is my project on image quilting and texture synthesis. So the goal of this project was to start with a small texture and then expand that to a larger synthesized version of that texture. And so there are three versions of the quilting algorithm that I implemented that I will go into further detail in a second. So the first version that I implemented was the random quilting. I divided the output of the grid into square patches, and for each position, I just picked a random patch from the input texture to paste in. This is like a baseline method and it's very simple, but there's no attempt to like line up the patterns. And so you can very visibly see that there's squares visible and it looks very disjoint. So the second version was the overlapping quilting. Here, each new patch overlaps with the ones already placed, either to the left, above, or both. And for every possible patch position in the sample, I compare just the overlapping region and compute the sum of the square pixel difference, or the SSD. I then choose a patch whose overlap error is small so that the new patch blends better with its neighbors. And so here we can see there's a much better natural look to the overlapping version, although you can still tell that there are some boxes here, and this will be kind of dealt with by the seam finding function. It starts in the same way as the overlapping quilting by picking a good candidate patch based on the SSD, but inside the overlap, instead of just blending everything together, it treats the square difference as like a cost image. It finds a minimum cost path through it. Then the path like kind of tells you where to switch from the old pixels to new pixels, so the seams become much less visible. The transition from the overlapping function to the seam finding function is so much better. So this side-by-side comparison shows how good the algorithm is and how transition between these functions actually makes the image look way better. So this figure is kind of illustrating what the seam finding step is doing. On the left is the overlapping strip from the existing patch, and the middle is the overlapping strip from the new patch. And so if we subtract them and square the difference, we get the cost image to the right, where brighter pixels mean a bigger mismatch. And the seam finding algorithm pretty much finds a path from the left to right that minimizes the total cost while only moving up, down, or straight. And then the path is like drawn in red right here. So before going into some of the examples of the images that I was able to generate, I wanted to go into the implementation choices that I had specific to my code that I made. So firstly, when I computed the SSD, I only looked at pixels inside the overlap mask, and this follows the idea from the paper, but also keeps the computation focused exactly where we care about continuity. And then secondly, when I chose a patch, I didn't always look at the single best SSD value. I instead collected all the candidate locations whose cost is within a factor of like 1 plus like the tolerance of the minimum, and picked one at random. So this kept the texture from looking repetitive, but still respected the best matches. And third, I wrote a single seam finding function and reused it for both horizontal and vertical overlaps. I remember in class that we spoke about near regular images versus like stochastic images. And so I wanted to have a split difference between these two and see what the effects would be on the generated images. And so we have an image of the weave. You can see that seam finding did a pretty good job of expanding it. There's not really that many flaws. Same with this leaf image. I think this is the best one that I worked on. You can't really tell at all where the repeats are in the samples are being taken, or even where the seams are. So this is an example of one of the images that I took, and it's way less uniform than the other examples that I gave. The seam finding function still does a good job of being able to generate a larger version of the QR code that I provided. And then this is the second picture that I took. This is probably the highest variation in the texture of an image that I've provided to this function. And we can see that the quilting algorithm still does a very good job of making a general picture of this. Obviously, because of the ununiform nature of the image, there are going to be sections of the picture that end up looking irregular, like the ones that I'm highlighting right now. But overall, the image does resemble the sample that it's taken from. So regarding the strengths of this algorithm, obviously it worked very well on regular images, but it was kind of weak when it came to stochastic or like less uniform images. But even so, it was able to kind of generate a generalized texture of the given images. And so an application to extend this would be to apply it to a texture transfer onto arbitrary images. Thank you so much for listening to my presentation.